Okay, so the first thing I'm doing here in proofs with rationals and irrationals, I'm reminding myself again, what are the definitions of rationals or irrationals? So a rational number is a number of the form p over q, where p and q are integers, and q is not equal to 0. So that's a rational number. Irrational would be any real number that can't be written in this form of a ratio of two integers. So irrational, so this is rational and irrational. I might just write down some. I know pi, I know e is about 2.7182 blah blah blah, 3 point about equal to 3.14. Maybe I know square root of 2. Um, anyway, I don't really know too many. That's okay. I'm just going to see what I can pull from. So I'm trying to see if I add two irrationals, are they going to be irrational also? Well, if I add pi plus e, I'm not really sure what that would be. E plus e would be 2e. That would be irrational, but I'd start to get into I'm just not really sure. And then I think about, okay, can I twist it at all? Can I do anything creative to get to a rational that I do know? Square root of 2 plus square root of 2 is 2 times square root of 2. That's square root of 8. That's still irrational. Um, oh, what about pi plus negative pi? So I might say disprove. Consider pi and negative pi. Or I could have said consider x equals pi and y equals negative pi. Either way, this would be a complete proof then, because I've found a single counterexample so that I know that maybe sometimes it's irrational. Certainly I found a couple examples where it was, but all I needed was a single example. When I add these two irrational numbers, then I get a rational number of 0. 0 is certainly rational because 0 over any integer is a valid fraction there. Okay, what about this next one? If x is irrational and y is rational, then x plus y must be irrational. So maybe I think of, again, pi, and then 0 is rational. And this would give me pi, which is irrational. So it works in that case. I know at least one case where this works. I may play around with a couple others. And let's say I start to believe that it is true. One way I can do this is a proof by contradiction. So I'm going to actually say this so I don't shock the reader. Proof by contradiction. Let x be rational. Oh, sorry, irrational. Y be rational. And or I could even do this, such that x plus y is irrational. Sorry, x plus y is rational. I'm going to try to come up with a contradiction here. So I want to assume the negation of what I'm trying to prove. So let x be irrational, y be rational, such that x plus y is rational. So y equals pq, and x plus y equals rs for P, Q, R, S in the integers with Q and S not equal to 0. So I'm just invoking that definition again. So how's this going to help me? Well, if I say y equals, actually let's do, sorry, x equals x plus y minus y. Basically what I'm doing, I'm taking the formula x plus y equals x plus y, and I'm solving it for this particular y, for this particular x here. So x equals x plus y minus y, which equals r over s plus p over q. Now I'm just doing substitution from my line above. And this equals, I'm getting common denominators here so that I can add these two fractions. And suddenly what I have, since QR plus PS is an integer, and QS is not equal to 0. Now remember, I have Q not equal to 0 and S not equal to 0. So the only way a product would be equal to 0 of two integers would be if one of the two, at least one of the two, was 0. So since neither one are equal to 0, we know that the entire denominator is not equal to 0. We have x is rational. But we assume that x would be irrational. So we have a contradiction, and thus x plus y must be irrational. Okay, and just to go over that again. So I'm thinking this is irrational, this is rational, and this is irrational. So two of these three are of a form that I can't really deal with algebraically very well. Rational numbers I can put into this nice fraction, and then I can do any kind of arithmetic with fractions. So I'm thinking the reason I'm choosing a proof by contradiction here, one, because I think it might be a true statement, because I've tested maybe a few examples and it's seeming like it could be true. And two, if I do a proof by contradiction, I can assume that one of these, or that this one here, is rational, which means that two of the three things I'm working with, I'll be able to put in some algebraic form. And that's great because I can just solve for the thing that isn't in algebraic form. If this is in some fractional form, this is in some fractional form, I can deal with those algebraically to solve for this. And my hope is that I can prove my assumption false. So I'm making this assumption that x plus y is rational, and I'm hoping to prove that false. So when I set everything up, I basically have x plus y equals x plus y. This is a irrational, this is a rational, and this is a rational. I have something like this. So I'm just subtracting this rational from both sides. Then I'm just adding and subtracting rationals. In fact, I could say the rationals are closed under subtraction, which means this has to be a rational. That would have been an even simpler way to call back on those theorems at 2.1 or 2.2, whatever they were. So with that in mind, either way, I'm going to prove that this right here is rational, which is a contradiction because we know that x is irrational, not rational, and that's where my assumption comes in. My contradiction comes in. Whatever I assumed is now going to be incorrect. And what did I assume? I assumed that x plus y is rational. So that assumption must be incorrect, and x plus y must be irrational. So that's example of sometimes you get an easy one, sometimes you get one that you really have to do some work for.